Hello, chemistry students. So we're going to start now a lesson on how we can predict redox reactions, and from this prediction, then calculate what might be the standard cell potential. Now we're going into a future discussion on batteries, so it makes sense that we talk about now voltage and potential, or voltage potential, or half potentials of these half reactions that we've mentioned in the past. So let's get started. But first, we're going to remind ourselves that of a few things, namely Leo the Lion says Gur, remembering that losing electrons means oxidation and gaining electrons means reduction. And a couple more definitions related to that. Reducing agents, they're the agents that cause reduction reactions. So they're going to cause reduction reactions, and they do that by giving electrons giving electrons away. Thereby, what's happening is that they're getting oxidized themselves, but they're causing the reduction of something else. Now, the opposite is also true. Oxidizing agents, they are the agents that cause oxidation reactions. They themselves, however, are being reduced. So they gain electrons, right? They gain, meaning they're being reduced, but they're the ones that cause the oxidation, thereby calling themselves also oxidizing agents. Okay, so a few important definitions to remind ourselves of. Now, also recall from grade 11, last year you looked at the activity series or reactivity series of metals. So this table should be familiar, something you worked with to predict single displacement reactions, which was a prelude to what we're about to do right now. And just a reminder that the higher on this list an element or metal is, the more reactive it was. There's a little bit more to that. We can say that now that any element on this list that is higher near the top is easier for it to be oxidized, right? So the easier this metal is going to be oxidized. So anything lower in this table, the easier it is for it to be reduced. Okay, and there is more to this table. Don't mind that. Another reactivity series or version of this table is here. This time it's written with these half reactions. Now we're going to see the more important table on the next slide, but before we do, I'll talk about that table. Perhaps should have shown it here, but this is just a prelude to that. So the further apart half reactions are, again, you'll see this in just a bit. So the further apart these half reactions are, the faster it's going to be, the faster this redox reaction is going to be, and the more spontaneous it's going to be. Now, a spontaneous redox reaction means you have electrons flowing from one metal. So one metal is going to lose, another one is going to gain. So to create a flow of electrons, and that is called current, right? Think of current as the amount of water flowing down a river, where the voltage is at one point, how much water is flowing per unit time. Okay, more on that near the end. So just as a reduction reaction is the sum of the reduction half reaction and the oxidation half reaction, if you add the two voltages of these half reactions, measured half reactions, we get the overall potential of that cell or of that battery, the cell in that battery. And again, we'll talk more about that in our next lesson. Okay, so a lot just said right now, but it should make hopefully a bit more sense as we then begin an example. A few more points though. Okay, so this is that table. Okay, so here's that table. Now this is a standard reduction. The keyword here is, well, lots of things happening here, but the keyword is reduction. So these are half reactions written in their reduction form. That means you can see everything here gaining an electron, right? Gaining electron means reduction. Everything here gains an electron, so it's written in their reduction form. Notice this double arrow here, it can be reversed. In fact, we'll do that as we do examples. Standard means it's standardized at 25 degrees Celsius temperature, measured then these standard potential or standard voltage of these half reactions all along here. Another thing to note is that the standard hydrogen potential right over here, I just look for the 0, is just placed for reference. Anything above that is more likely to be reduced, right? Therefore, a good oxidizing agent. Anything lower in the table is going to be a good reducing agent. In other words, oxidize. So oxidation reactions, half reactions, oxidation reactions happen at the bottom of the table more likely, where at the top of the table, reduction reactions are more likely to happen. Okay, so we talked about the table. We talked about how redox reminded you how redox reactions should work, flow of electrons, then briefly how we're going to calculate this voltage potential across two half reactions, a reduction and an oxidation half reaction. Okay, now let's look at our first example. So here we're just going to compare, right, and also predict in doing that. We're going to compare the copper, copper 2 ion and zinc half reactions from this uh, reduction table, reduction potential table. Okay, now this table is not complete, I should say. This is a shortened version of it. You have a full version on page 729 in your textbook. So for any questions that are assigned, or even the last example in this lesson, I am referring to page 729, which is the complete table you'll need to use. But for now, we're just going to use this. Okay, and I'm going to make sure to answer these questions as I compare these two half reactions. Which are the oxidizing agents, which is the oxidizing agent and reducing agents, which are, and explain then how electrons move from what to what. And we can also then calculate, since we're already at it, the total cell potential, the total standard cell potential. Okay, so let's look for the half reaction involving copper 2 ions. So looks like it's right here, copper 2 ions right here. So I'm going to write that down. Okay, and that has a measured 0.34 standard voltage potential. Okay, and zinc is right here, just below it. And that has a measured, not positive, measured negative 0.76. Okay, so now let's analyze these two. Our first reaction, let's call this reaction 1, reaction 2, half reaction 1, half reaction 2. Okay, the first one is closer to the top. So it's likely going to be a good oxidizing agent, right? So number 1 is likely a good oxidizing agent, right? It's also, if it's a good oxidizing agent, it's therefore also going to be reduced. Okay, number 2, lower in the table, it's likely a better reducing agent. And is therefore going to be oxidized. Okay, right. Now, if you look at 2, we can see that 2 is written in its reduction form. Now, we know this double arrow means it can go left and right, so we should actually rewrite this. I'm going to rewrite 2, I'm going to flip it, and it's going to then look like this. Right, and because I flipped it, I should also change the sign. I'm going to flip that sign, so it's going to be positive 0.76. Okay, now the last thing I should do, well, almost last thing I should do is I should now look at my reduction half reaction right here and my oxidation half reaction right here. And as we've done in previous lessons, we're going to add them. So if we add them, we'll see that, I know it's a bit, this is right in the middle, but if you look at the left-hand side compared to the right-hand side, you can see that you're going to cancel out the 2 electrons. And all we get here is we're now going to add anything that's remaining. So Cu 2 plus and zinc. Let's cancel that. You know what? I'm going to erase this here, scratch that out, and I'm going to rewrite it over here. Okay, so Cu 2 plus zinc. So Cu copper 2 ions plus zinc. Then we have our arrows. Okay, we excluded electrons since they're canceling each other out. There we go. So this is our redox reaction. Okay, now our redox reaction will create an overall potential, which is just then the sum of, we add our standard potentials of both half reactions. So here's standard potential, then of our reduction reaction, plus the standard potential of our oxidation reaction. So the standard reduction potential is 0.34, 0.34, and the standard oxidation potential, remember we had to reverse that and change the sign, is 0.76, and we get an overall standard cell potential of 1.1 volts. Okay, so there are a few things we reviewed here. Our oxidizing or agent, our reducing agent, but first take a step back. This is the reduction reaction. This is the oxidation reaction. So this is a good, copper would then be, copper is then your oxidizing agent. Zinc is then your reducing agent, right? And we know that Leo the lion says grr. So if we lose electrons, right, whatever is being is whatever is oxidized then loses electrons. So our reducing agent is what's actually being oxidized. Our oxidizing agent is what is being reduced. So the flow of electrons is from oxidation to reduction. So electrons travel then from zinc to copper. And the overall potential of this redox reaction is 1.1 volts. Now for a real example, because this wasn't really, I didn't write example here, because this is just looking at two half reactions, and we're seeing then how the table works. We're defining what's being reduced and what is your oxidizing agent, what is being oxidized, and then of course that is your reducing agent. So we're reviewing these half reactions and how to use this table. Our purpose then is going to be in the next example is to determine if a redox reaction is going to be spontaneous or not, and then also to calculate the total standard cell potential right, as a sum of the two half reaction voltage potentials. Okay, reduction and oxidation. If looking at your table, so back to our table, if we can do this, if we can take copper, circling that right now, if you can take your copper ion, copper 2+ ion, and that is your oxidizing agent, right? And if you can also take what is being reduced, or what is your reducing agent, right here. Okay, this is, of course, if you reverse it, it's going to be your oxidizing, rather your oxidation reaction. So if you can take these two, right, and draw a line, a downward diagonal line like this, then it's going to be spontaneous. If you can't draw a downward diagonal line, meaning it doesn't have a good, on the left hand side, top of the table, it doesn't have a good oxidizing agent and a good reducing agent. So if that line can't be drawn, then it's not going to be spontaneous. Okay, but in this case, a good oxidizing agent, a good reducing agent will create that line in the downward diagonal, downward to the right, making it a spontaneous reaction. Okay, again, this is our reducing agent. Notice I should clarify that here. This is our zinc, is our reducing agent, right? Copper 2 ion is our oxidizing agent. Yes, a line can be drawn the downward diagonal to the right. So yes, this is spontaneous. Okay, we've broken that down into its details. Now let's get into our example. These are steps on how to predict if a redox reaction is going to happen. I'm not going to read over all of these, right? Let's put into context and let's start this example. Okay, so your first step First step is to list all of the entities present. So step 1. Okay, we have from our reaction, or from our question, we have copper metal, so this is solid copper is placed into solution of nitric acid. Okay, so we have, let's write this down. We have solid copper, all right, we have nitric acid. Okay, and we know that AQ means that this exists inside water. So we have water present here because water can play a role, and we're going to see if it does. So this is the situation we have now. Is this a spontaneous reaction? B, what is the redox reaction? So we're going to take, once we figured out what our half reactions are, that is assuming it's spontaneous, you're going to add them together to create or to write our full redox reaction. Finally, then what is a standard cell potential? We can take the two half reaction voltages and then add them together. Again, assuming this is spontaneous, and we've answered these 3 parts. Okay, so first we've identified what all of our entities are. Next step, classify the entities as either oxidizing agents or reducing agents. Okay, so I took the liberty of going to page 729 in your textbook and taking a screenshot here of the relevant parts. You're looking for copper, you're looking for nitric acid, and anything else that's present, in this case water as well. And you're looking for whatever appears on the top at the furthest ends of the table, so the very top of the table and the very bottom of the table. Here we have, let's start with copper. So solid copper. The states are really important. States are really important. You want to make sure to look for states because you could easily confuse this with something else. So solid copper is found right here. This is at the bottom of your, or closer to the bottom of your table on page 729. I believe this part is on page 730, so just flip the page. And nitric acid is on 729. It's higher than solid copper is. You can see nitric acid broken up into its ionic form is right over here. So immediately you can figure out if this is spontaneous or not. Look, you can draw, well, let's see, let's talk about it a bit more, but you can draw a line, the downward diagonal to the right, meaning you have a good oxidizing agent and a good reducing agent. So here is your good oxidizing agent and here is your good reducing agent. So first part is, yes, it is spontaneous. Okay, so we can write since HNO3 is a good oxidizing agent, no comma there, and since solid copper is a good reducing agent, therefore the reaction is spontaneous. Okay, first part is done. Let's write these reactions. Well, I have them written here, so I'm going to write them in our next slide. What we're going to do now is finish answering this. What is it is spontaneous. What is the redox reaction? Okay, I have some room here. Let's just do that here. Okay, we can write our half reactions. I'll have to rewrite it in the next slide, but at least I can get started right now. Okay, I should say, as I'm writing H2, I realize water is found, I think it's right here actually. You can kind of see that I cut a bit of it out. Water is found in the table, and it wouldn't work as a reducing agent because if you notice, it's on the left-hand side, right? It's not a good reducing agent. Reducing agents appear on the right-hand side, right? To draw that downward to the right diagonal arrow or a diagonal line. So H2O is actually not involved, not part of the redox reaction for that reason. Okay, I'm just rewriting this oxidation or oxidizing agent half reaction, and I'm going to write the reducing agent half reaction. Okay, so these are the two reactions we are going to consider. And we will have to rewrite them in just a bit, change them around a bit. Okay, I should go over our steps though. So step 2, I'm going to rewind for just a bit. Step 2, we're using the table to identify, so that's done over here. We're using the table to identify our oxidizing agents and reducing agents. right? That was done. We're going to identify the strongest oxidizing agent to the top left and the strongest reducing agent at the bottom right. We've done that. Step 3 right over here to then predict if it is spontaneous. Step 4, predict whether the reaction is spontaneous. Yes, it is. Step 4, it is spontaneous. Okay, write the half reaction equations, and this is where we're going to continue on the following slide. We're going to reverse the direction of the oxidation reactions. So 1, 2, 3, 4, 5. We're going to continue on the next slide, and we're going to then have to multiply, or rather balance the electrons. So I wanted to rewrite them because I need to point out that electrons in both ends, this is the reduction reaction here. This is drawn as a reduction reaction, but we know that this is our oxidation reaction here. So it doesn't look like an oxidation reaction because we have to flip it. It's written in its reduction form. So we're going to have to flip this. So let's use the next slide to do that. So the reduction reaction is just fine. You can copy that down as it appears. Not too. Okay, and that flipped reaction is your oxidation reaction. So we have solid copper okay, and 2 electrons. Good, so this was step 5. Now step 6, we're going to need to make sure that electrons are balanced. Now if we see here we are gaining electrons, 1 electron, and here we're losing 2 electrons. The electrons here are not balanced, so we're going to have to multiply the half reaction, or maybe not just 1, but it could be 2. In this case, it's 1. Multiply the half reaction by 2. To balance electrons. So we're going to multiply everything in our reduction reaction at the top by 2. So it's going to look like this. Okay, and we're going to leave copper alone. The oxidation reaction won't need to change. Okay, so our last step is going to involve adding these 2 reactions. Now notice that on the left-hand side we have 2 electrons leaving, or being accepted, I should say, 2 electrons being accepted. Here 2 electrons being donated, so those cancel out. 1 on the left, 1 on the right, they cancel out. And everything else we can rewrite as our combined redox reaction. Okay, so this is our full redox reaction. And that's our 7th and last step to write the full redox reaction. But we're being asked for one more thing. What is the standard cell potential? Okay, we can fit that right here. Now the standard cell potential, so this is part C of the question. Remember, it's okay, so it's your reduction half reaction potential plus your oxidation half reaction potential, not half reaction potential, yes. You add these 2 voltages. Now I didn't write them here, but if we go back, perfect, it's right here. If we go back, we know that the half reduction potential is here. This is for the reduction reaction, 0.96. And we're going to add, now this is where you want to be careful. This is also 0.34 is the reduction half potential of this reduction reaction. But because we reversed it, we have to change the sign. It has to then be negative. So 0.96 plus a negative 0.34 would then be our total standard cell potential as at 0.62 volts. Okay, so we've done that work to do two things. To realize that, yes, this is a spontaneous reaction. This was part A, right? Part B is a conclusion at step 7. This is our full redox reaction. Part C is our standard cell potential involving adding the half reduction potential and the half oxidation potentials for a total then of 0.62 for your total standard cell potential. Okay, so this is where you can find the required reading for that will accompany this lesson, and some practice work. Ask questions. I'll post solutions to another example. Should also say that I have a study guide that goes along with this lesson, so you can follow along. This example here was taken straight from that. There is another example, and I'll post answers for that. I hope this helps.